Hey, AP Physics C students. Today we're going to take a look at H3 standard charge densities, and we're going to talk about that, and we're going to be reading up to Gauss's law. So the first thing you have to understand about charge densities is that when you have charge on an object, charge spreads itself, especially along a conductor, continuously along its surface or along its volume. When you have charge densities, what we have a way of doing is identify how much charge is on an object and relate how dense the charge is on any particular area based on the shape of the area. So we're going to look at a few different sorts of charge densities, and we're going to define charge densities as a continuous amount of charge that's distributed uniformly over dimensions. So we're going to look at three dimensions. We're going to look at linear versus an area versus a volume charge. So when we have that charge density, we're going to look at it for charge per unit shape. And the charge density, we're ultimately going to be looking at ways to use integral calculus to do this. So we're going to write charge densities as differential equations at times, even though we're going to look at them most primarily algebraically. Let's look at a first charge density. This one is going to be one-dimensional charge density or linear charge density. I want to be clear about this when I talk about one-dimensional charge density, that even though we're going to be identifying charge in charge per unit length, the shape itself does not need to be a line. We're going to look at wires, we're going to look at straight lines, but we'll also look at things like rings or semicircles, anywhere where the charge is just one-dimensional, even if that linear is, or even if that string of charge that has no width is bent, we're still going to look at it as a charge density. So our charge density symbol is going to be lambda. We're going to say that that charge density is going to be charge per unit length. And if we wrote that as a differential equation, it'll be lambda, or the charge density for linear, is going to be the dq/dl, or the change in charge per unit length. Both of those are just telling for any particular length of this item how much charge is there. So if you know the lambda, you could identify that's how much charge would be in, like, say, 1 meter of its length. Or you could take that same charge density, and if you did a half meter, you'd be able to find half the amount of charge. So it's telling us just how much charge is per unit length. Two dimensions, we're going to use the lowercase sigma, and that's just going to be charge per unit area. And the differential equation is going to be dq/dA, or the change in charge per change in area. And then if we look at this in three dimensions, in a three-dimensional charge, this is going to be charge per unit volume. At least note that when you talk about charge per unit volume, this obviously cannot happen on conductors, because conductors would carry their charge on the outside of their surface. So when we talk about charge densities for volume, these will only occur in insulators where the charge is held in place because the insulators doesn't let the charge move. As a differential equation, that's going to be rho, the charge density operator, is equal to dq/dV. So here we have our three charge density operators. Now we're going to take a look at an example of charge density. So in this example, we have a thin conducting wire that is 3 meters long, and it's given a charge density of 1.5 times 10 to the negative 6 coulombs. We want to figure out what the charge density is along this wire. To do that, we're going to take a look at the lambda. This is going to be Q over L, and we have a charge of 1.5 times 10 to the negative 6 coulombs, and then that's spread over 3 meters of length. So if you do 1.5 times 10 to the negative 6 divided by 3, you end up with 5.0 times 10 to the negative 7 coulombs per meter. So every meter of length for this wire will give you 5 times 10 to the negative 7 coulombs of charge. So if you multiply the length of any wire by your charge density, you're going to figure out how much charge is encased there. Let's do another example of this. In this example, we have a ring of radius 0.15 meters that's given a charge of 1.2 times 10 to the negative 5 coulombs. And we want to find the charge density here. Now the shape of the ring is a circle, but our charge density operator, is going to be linear, because what we're going to do is we're going to say how much charge it has per unit length, even though it's arc length instead of a straight line length. So here we're going to do charge enclosed, which is 1.2 times 10 to the negative 5 coulombs of charge. And here we have our length. Now the length is going to be the circumference of the circle, which is pi times circumference, 2 pi times radius. And then we're going to find that the charge density here is 1.3 times 10 to the negative 5 coulombs per meter again. So this is how we would find the charge density of a circular object. These last two, we're looking at the charge density, and you see this in your notes. And I would encourage you to try to find the charge density of a hollow conducting sphere. In this scenario, you have 1.2 coulombs. The radius of the sphere is 3.1 meters, so you'd have to find the surface area of a sphere. And this is in your notes, and you can find this here. And then lastly, here we have a charge density for volume. Here you'd have to use the volume of the sphere, and here's the answer for that one as well. So I would try these last two, and you see the answers up here on the screen. So try those two in your notes. Make sure you can come to these, and then move on to the next section.